Hi everybody, this is going to cover section 4.6, which is about again, direct proof type of argument, but using yet another definition. The thing we're after today is the floor and the ceiling functions. These are two different functions that are, well, they're related to one another, but they go from the real numbers to the integers. So in terms of the range and domain, it's the reals are the domain and the integers are the range. What they are is basically rounding down or up. That is, you take a real number and you either move it down to the next integer, the first integer under it, or you move it up to the next integer above it. The formal definition and the notation for it looks like this. You put almost absolute value bars, but with those little feet on it. That means the floor. And ceiling is similar, but with the little dashes, the extra things at the top. You have x like this. So floor of x would be equal to some integer y, or ceiling of x would be equal to some integer y, based on basically two things. Let's see if we can write these in parallel. If and only if. Well, first of all, I need y to be an integer. And I want y to be the integer just smaller than x. So I want to have y be less than or equal to x. The problem is if I say that doesn't get me the thing just smaller than x, but it gets me everything that's just smaller than x. This wouldn't be well defined that way. But if we also cap it this way and say that y is less than or equal to x, but y plus 1 will definitely be bigger than x. Now you've uniquely determined what y is. Okay. The ceiling is very similar, just a slight difference in how the inequality is written. So you want y to be an integer. I left out the and. That's supposed to be an and connector there. Actually, gosh, in this class, we know the symbol for that. I should have written like that. Well, y is in z, and so if y is going to be the ceiling of x, the number just bigger than x, then x is capped from above by y. And so what's the thing that's going to be on the left of x that guarantees y is unique? Actually, this one, it would be y minus 1. Like I wrote this, somehow the drawing of it is awkward. Oh, darn. Well, I just looked back at the book, and they did the same definition, but they called this number n, which actually kind of makes sense. N is typically reserved for numbers that are integers or natural numbers, and x's and y's would typically be reals. But except for a change of variables, this is the same definitions that are given in the book. Probably a quick example of each of these is in order. Well, let's just do it with regular numbers. If I have the number pi, which everybody should know is 3.1415928 something or other after that, and I take the floor of that, what am I going to get? That's the whole number 3. What about if I start with an integer and I want the floor of that? So if we think of y as being, so x is 7, what should y be? Well, you want to concentrate on this inequality. If x was 7, how about y would be 7 too? Because these two being equal would satisfy the less than or equal, and then 8, y plus 1, would be definitely bigger than x. Seems like 7 would work for 7. And that's sort of an important point to recognize. If you've got a whole number, when you take its floor, it doesn't do anything. It's only when you have a number that's just off from being a whole number, like 3.14, that'll get rounded down. On the other hand, if I rounded the number pi up, what would I get? Well, you wouldn't get 3 because it's already bigger than 3. You'll have to pop up to the next number, which is 4, the next integer. How about if I round up the square root of 3? You have to know the square root of 3 is like 1.7 something, and if you do know that, then just rounding up will get you to 2. Okay. One thing that so often comes up is you think about, what if you do these things one after the other? Suppose I have a number x and I round it down, and then I take that and I round it up. What would that be? Well, that's exactly the same thing as the rounded down x, because why? Once you round it down, you're at an integer, and the ceiling of an integer is that integer, just like the ceiling of, just like the floor of an integer is that integer. So, yeah, there's a neat simplification you can do. Suppose I looked at the floor of a sum of two things. Would you say that this makes sense? I'm asking a question, really. That if I have the floor of two guys rounding down the sum, basically, I could round down each of them separately and add those two things up. In other words, can we sort of distribute this floor across a sum? What do you think about that? Well, a good way to look at statements in general is to look at sort of extreme cases. Like if x was equal to 1.999, then the floor of x is 1, right? But this is a place where the floor has made the biggest potential difference. I've taken off almost a value of 1 from it, changed the result by 0.999. That's a great hint. What if we make both numbers be kind of extreme like that? Y also like 2.999. Then the floor of y would be 2. Well, what's x plus y? Here's where estimation will help us. That's basically 2, and that's basically 3, and 2 and 3 is 5. So this is just a little bit less than 5. Actually, it's 4.998. All right, so what's the floor of x plus y? Well, it's 4. But x and y's floors separately are 1 and 2. And that's not the same as 4. Sorry. Right? On the sum of the floors, we get 3. On the floor of the sum, we got 4. They're not equal. There's actually kind of a nice proof that we should do where if one of these actually is a natural number, then this does work. And so let me show you this one, because it's good to sort of explore the boundaries. We've seen a case of a reasonable looking rule that turns out to be false in this setting. How does it change if I make one of the things a natural number? This is a theorem. For all x in the reals, for all n in the integers, the floor of x plus n actually is equal to the floor of x. Well, I was going to say plus the floor of, let me write it that way first. Floor of n, but you could almost immediately say, yeah, but this is an integer, so the floor of n is n itself. So, all right, so that means we can replace that floor of n with simply an n. Let's make the statement be this, so it's a little more clear. All right, so let me go for a proof of this. What's our initial boilerplate sentence going to be? We've got a particular but arbitrarily chosen x, that's a real number, and a particular but arbitrarily chosen n, that's an integer. I'm going to just say suppose x in R and n in Z suppose x in R and n in Z are chosen arbitrarily. Great, so then the floor of x plus n, let's start this with a then. Well, what does that mean? What does the floor of x plus n mean? And what shall we call it? We need a number to name this thing. How about this is equal to m, to distinguish it from n? Then is the wrong word to introduce this sentence. But how about suppose? Now we'll put a then in. What I want to say is that x plus n here satisfies that inequality that the floor tells us. Then m is less than or equal to x plus n, which is less than m plus 1. Cool. That's just from the definition of what the floor is. I wrote it down on the, I think, 2 screens back now. Well, okay. But what I would like to do is get something that says something about the floor of x plus n. How could I look at this inequality here and say, get the definition of the floor of x? Let me switch colors and just write a sort of a parenthetical note in the corner here. We're looking for something that looks like that we know what the floor of x is. We're looking for some p that's less than or equal to x that's less than p plus 1. So I'm asking you to stare at this and figure out how to get, basically to get rid of this plus n here. To get rid of a plus n, you subtract n. And you got to do it in this place and in this place. I'm also going to rearrange that to be m minus n plus 1. The n there. All right. Whoops, what did I do? I took away the n on the m. I didn't take away the n. That's why I ran out of space, I think. Sorry, let me just fix this with the eraser. The operation we were doing was subtracting n from each part, so x should end up all by itself in the middle here. And then m minus n plus 1. Yeah. Cool. So by the definition then, the floor of x is equal to m minus n. Right. But that's close to being the floor of x plus n, isn't it? That's equal to the floor of x plus n, which is m, minus n. All right, so unfortunately, this came out with the pieces reversed, but all I have to do now is add n to both sides of this. Floor of x plus n will be floor of x plus n. Sometimes my little feet on these things get out of control. Those are too wide. They're supposed to be little short dashy things. All right. Well, that's the result, except I guess I switched things. I should have had x plus n on the left. We could probably stop and pretty this up and make it work out a little bit better, but it's okay as it stands. It's a valid proof. So let's put the end of proof symbol. I think I'm going to leave the floor function there and get us a little start in section 4.7. There's a couple more proofs in section 4.6 that you might want to have a look at, but they're not huge. They're not too hard to follow. I think it may be the case that the definition of floor and ceiling are amongst the harder things for us to internalize, but if you play with them a little bit, there's homework questions about those, using those definitions, and you should get somewhere on it. The reason I'm actually anxious to get on to chapter 4.7 is just that finally we'll be doing something that's a different proof technique, something besides a direct argument. Well, in fact, the styles are called indirect arguments. The two things that we're going to look at. This is section 4.7. So there are two different types of arguments that are known as indirect. They're actually kind of versions of one another, but the way you lay them out seems different, so we sort of distinguish them. The first one is called proof by contrapositives. And the second is called proof by contradiction. So first off, let's do proof by contrapositive because it's easier. So if we jump into proof by contrapositive, if you start a proof that's a proof by contrapositives, your first sentence will be this: consider instead the contrapositive statement. And then you'll write down whatever the contrapositive statement is. And generically, it'd be something like not Q implies not P. Oops, not P. I don't know what that, in different particular situations, this would be different statements. It's kind of strange, but this is a really valid way or valuable way to argue, because sometimes P implies Q. The truth of P doesn't get you anything. It doesn't give you some machinery to try to work with to move on to proving that Q is true. But if you look at not Q, instead, you get traction. So my favorite piece of advice to people that are trying to write proofs: if you're stuck, look at the contrapositive. It's really good advice. Sometimes the contrapositive will be really easy, and the original sentence not so much. So. But why don't before I launch into talking about proof by contradiction, let me give you an example of a proof by contraposition. This is the statement I want to have us take a look at proving. If you've got an integer x and you know its square is even, that implies that x itself was even. Something a little bit backwards about that. So if you thought about proving it, you know, your first part would be to assume x squared is even. And then you'd get a therefore or a thus x squared is of the form 2k for some k in the integers. Okay. And now where are you supposed to go? I'd like to show, what I'm trying to get at is that x is even, so I want to get that x looks like 2 times something. Obviously it's not going to be k, but something. So what would you do next? Well, I guess you would take the square root, which is root 2 times root k. I can do that. Wait a second. Root 2 is not an integer, and root k might be, but it certainly isn't guaranteed. That is so ugly. Let me try that again. A k in there. Yeah, root 2 is certainly not an integer, and root k might be or might not be. This is not even, well, the only reason we know this whole thing is an integer is because we already assumed x was an integer. But wow, how would we work with that expression to try to write that x is equal to 2 times something? Here's the question. Could we get from that to saying x equals, say, 2 cubed? Is that a possibility? I sure don't see how to get it. So let's instead look at the contrapositive. Let's just box this stuff up. So that was a failed attempt. Didn't work. Let's see if we can actually write a proof. Consider instead the contrapositive statement. And what is that going to be in this instance? Well, the original thing was x squared even implies x even. We got to flip the order around, but also change these further negations. Now, in the integers, you could say x is not even implies x squared is not even, but I kind of prefer to just say odd. So the contrapositive statement would be this: x is odd implies x squared is odd. Well, that actually is easy. We've got the right direction for the computation. Assume x is odd. So suppose x is a particularly but arbitrarily chosen odd number. I'm just going to say suppose x is odd. Then x looks like 2k plus 1. That's for some integer k. I should probably add that to the... And I'm going to leave the bottom half of the board unerased, so that'll be the proof we're working on from there down, but we'll continue from the top of the board. X equals 2k plus 1 for some integer k. Then, well, we're going to want to look at x squared. X squared by substitution is equal to 2k plus 1 squared. And that pretty easy example of the working with polynomials stuff we did last time. That's 4k squared plus 4k plus 1. And finally that can be written as 2 times something plus 1. What would the something be? 2k squared plus 2k. Well, I think that's pretty clearly an integer by the closure axioms. So since 2k squared plus 2k is an integer. Plus 2k. What we've got there is the definition of x squared being odd. Personally, now I say QED at the end of my proofs by contraposition. At this point, some people like to have a wrap-up sentence. So a wrap-up sentence might say, since we've proved the contrapositive of our original sentence is true, and contrapositive and the original are logically equivalent, it follows that the original sentence is true. I don't think that's necessary. But some people put something like that in there. It's personal preference. Myself, I would just say, here's the end of the proof marker. All right, let's do this last type of indirect argument, a proof by contradiction. All right, so proof by contradiction. This is frankly one of the most useful ways to prove things, and it's a little bit of a mind twist. You have to really get used to how this works. So let me just try to lay it out for you in steps. The first thing you do in a proof by contradiction is you assume the exact opposite of the thing you want to prove. That is, you assume the negation of whatever the sentence is. From there, you are going to argue or reason on purpose until you get to some ridiculous conclusion. One word that people use for this is an absurdity, something that's absurd. But that's sort of an old school use. Most people today would say reason to arrive at a contradiction. I just wanted to put that word absurdity in your heads because this method is also known as, well, if you're in Latin, if you speak Latin, it's also known as reductio ad absurdum. And that's the word. That word means pretty much what it sounds like, reduction. Ad is the Latin, what's that called, a preposition to. So this literally means reduction to absurdity. Yeah, so what does it mean if we assume the negation of what we want to prove, and then we reason and end up with something that's impossible? It has to be that this initial assumption was false. You conclude that your initial assumption was bogus. That is, the negation of what you are trying to prove is false. Well, if the negation is false, what does that say about the original guy? Must be true. That's kind of an outline of the method. Assume the negation of what you want to prove, reason from there until you arrive at something crazy. And this start stage is the hard one. This is where the mind twist is involved. You have to pretend you're in a universe where the negation of the thing you're trying to prove is true. That's very counterintuitive. You know, there's a thing you believe is true, and you say, well, nope, the exact opposite of that is true, and pretend that's the case. Reason from there until you get to you make it clear that that leads to something ridiculous. So then you unwind that and say, okay, well that means the original assumption is wrong. That means the original thing before we negated it must be true. I think we better do an example. So this is Theorem 4.73 in the textbook. I've written it in formal logic terms, but it's a good chance for us to convert something from formalized stuff to I want to say common language, but we're going to be using words like rational and irrational, so it's still technical language, but anyway, ordinary English as opposed to all symbolic. So we're quantified over all pairs of real numbers, but then we immediately make a restriction that if x is a rational number and y is not a rational number, and then we conclude that the sum, x plus y, is not a rational number. The way you would say this in ordinary language is the sum of a rational and an irrational okay, that was the worst n of all time. What are you going to get if you have a rational number, something that can be written as a fraction, and an irrational number, so something you can't express as a or b? If you add those up, it will be irrational. Now there's plenty of mixes of these words you could do. So for instance, you could say the sum of an irrational and an irrational is, and it turns out in that case, you can't conclude anything. Sometimes it's rational, other times it's not. But here's one where we can make a solid conclusion. How do we go about doing that? Well, let's start the proof. When you're using anything besides direct proof, I advise having a little parenthetical remark after the word proof where you tell people what method you're using. So, by contradiction. They would, if they know what they're doing, they would get that from your first sentence, because your first sentence in a proof by contradiction is assume by way of contradiction that, that is, we want to assume the negation of what we got here. One of my favorite ways to phrase this is assume, comma, to the contrary that. Yes, that's the phrase, to the contrary that. All right, well, now we face the central problem of proof by contradiction. You've got to be able to negate the thing you're trying to prove. And what we're trying to prove here is an if-then sentence with x in q and y not in q. Those are the antecedent, and then x plus y not in q as the consequent. So how do you form the negation of an if-then? You say, if it's p, if p implies q, then you go p is true and q isn't. So the assumption should be that the whole if part, which is this thing about x in q and y not in q, and then the negation of this part. Okay, so let's collect that stuff. X will be rational. Y will not be rational. And let's make them all ands because they are. And lastly, x plus y, this one's being negated, so that will turn into x plus y is rational. Well, when you have three things ANDed together, you can pull out any of them and look at those and say those will be true, because all three of these things will be true at the same time. And the ones I'm interested in pulling out are that x is rational and x plus y is rational. why do I get that? Well, why do I want those two things? Because they let me conclude that y is rational. The difference, let me write down what the difference is and which order do I want to subtract them. I want to take x plus y minus x. The difference of two rational numbers will again be rational. Okay, well, we're done. That's great, because x plus y minus x is simply x. No, it's not. I don't know why I said that. X plus y, the minus x and the plus x kill each other off. What that is y. So we have just proved that y is rational. But it's also true from before that y is not rational. Now that is a statement together with its exact negation. And that's what it means to be a contradiction. I don't know if I have room for the whole word contradiction here. I'm going to make it tinier until I fit it in. Good. All right, so what is our, we should have a wrap-up sentence for our proof by contradiction. Usually people do. And what's it going to say in this case? Well, the original assumption that our statement was false led to a contradiction. Therefore, the original statement is true. There are many ways to phrase this. I'm giving you one example here. Assuming the contrary of the theorem, or contrary to the theorem, led to a contradiction, you conclude that the original theorem is actually true. A little word about the end of proof markers here. In the case of proof by contradiction, if you have finished off with a sentence like this, you would put the normal end of proof marker, whether you write QED or one of those colored in boxes. But a lot of times people will just state the contradiction. So, alternate ending might have been therefore y is in Q and y is not in Q. And they will make this symbol then to indicate the end of the proof. It's two arrowheads butting together. So that is just an alternative way you can do it. Just state what the contradiction is and make this symbol, which is meant to say, okay, we've got a contradiction, and therefore, the conclusion that's put into this sentence is just left tacit in that case. An amusing story. I used to have a professor I think it was in my master's degree, who, when he would get to the end of a proof by contradiction, he would go like that. And nobody in the class could figure out what the hell he was doing. And he was usually that sloppy about it. What he was really trying to do was make a single line and then simultaneously create the two arrowheads. But he was like, it looked like he was writing an asterisk. So my advice is to do like I did, literally separately draw the two damn arrows, because, you know, that's not saving you much and it's potentially leading to confusion. Don't do that. So, butting arrowheads means, okay, we've reached a contradiction, and I probably shouldn't tell you this last story, but I'm gonna anyway. One of my students a few years ago in an Intro to Proofs course, not this course, but Math 250, happened to really be interested in Latin. He had been learning Latin, and he said, we should come up with one of the Latin phrases for that instead of saying QED. What do you do when you get to a contradiction? And he came up with this. QISE. Which, if I remember correctly, was quod idem stercus es. And literally that means, what is this shit in Latin? It's much classier if you say it in Latin than it is if you, yeah. No, don't do QISE. Do the arrows, or else put in a sum up sentence and color in a box or write QED. Okay. All right, well that brings us to the end of section 4.7. So if you have questions about that, you know, maybe do some reading in the book. There is quite a lot in there. They've got outlines in the book about how to do the two different proof styles. And we are almost done with proofs. I hope that makes you happy, because we're going to go into some kind of fun stuff coming up next. All right, ciao.